Good morning. Good morning. So we've covered section 2.1 on linear first order equations. And today I'm going to talk about separable equations. So in our text, this is section 2.2. Separable equations. And separable means the following. The general first order equation we write in the form y prime is some function of x and y. So the highest derivative is the first derivative, and somehow we hope we can separate it out and write y prime as a function of x and y. But sometimes you can separate the variables x and y in the right-hand side. So you can write f of x, y as some function of x divided by some function of y. At least if h of y is non-zero. And if you multiply by h of y, you would get h of y, y prime equals g of x. So this is the general form of a first order separable equation. Separable means, again, you've separated the variables. All of the x's are on the right, all of the y's and y prime are on the left. So this is a separable equation. We have separated the variables. And when you can do that, there is a method to solve the equation. If not explicitly, then always at least implicitly. And if you took second semester calculus at Lehman and your instructor covered the syllabus, this was actually included, this was taught in Math 176. But I'm not going to assume that you know it because it's simple enough and we'll just describe how to do it. So what you first find are antiderivatives of the functions h and g. So suppose we let capital H of y be the antiderivative of h of y. That means that h prime of y, capital H, is little h of y. And we let g of x be the antiderivative or integral of the function little g of x. So g prime of x equals little g of x. So you integrate h of y and you integrate g of x, and you get these functions, capital H and capital G. And if you take the derivative with respect to x of h of y, by the chain rule, that's the derivative of h of y with respect to y times dy dx. That is h prime of y, y prime. H prime of y is h of y. So the derivative with respect to x of capital H of y is y prime h of y. And of course, the derivative with respect to x of g of x is just g of x. So what we have is that the derivative with respect to h, sorry, the derivative of h with respect to x is, h of y, y prime, is h of y, y prime. That is g of x, that's our equation, which is the derivative of g of x with respect to x. In other words, the derivative of h of y equals the derivative of g of x. So if two functions have the same derivative, they differ by a constant. H of y is g of x plus c. So in a certain sense, we've just solved this differential equation, at least implicitly. If we could solve this equation for y, we will have solved the equation explicitly. So let me just write down this formula again, and then I'll do some examples. But this is all there is to solving a separable equation. It's reduced to integration. You have to integrate these two functions, and you're almost done. So again, our separable equation of the first order is of the form h of y, y prime equals g of x. We find functions capital H and capital G that are antiderivatives. Capital G prime of x equals g of x. Capital H prime of x is h of x. And this equation has the solution that h of y of x is g of x plus a constant. So let's look at some examples. So in the text, this is example 2.2.1. We have the equation y prime equals x times 1 plus y squared. You might say that's not separable because I don't have x's on one side and y's on the other. Well, but you can rearrange this. You can divide by 1 plus y squared, which is never 0. 1 over 1 plus y squared, y prime, equals x. So this is my function little h of y, and this is my function g of x. So capital G of x is just the integral of x dx, which is a half x squared. And capital H of y is the integral of 1 over 1 plus y squared dy, which is the arctangent of y. So the solution of this differential equation, a solution y of x, is arctangent of y of x is equal to a half x squared plus a constant. Or if you just take the tangent, y of x is the tangent of a half x squared plus c. And that's the solution of this differential equation, Okay. Let's just check. What is dy dx, or y prime? When you differentiate the tangent, you get secant squared. So y prime is secant squared of x squared over 2 plus c times the derivative of a half x squared plus c, which is x. Let's see. How can we get from that back to our equation? I guess we have to remember some elementary trig. The basic trig identity is for any angle theta, sine squared theta plus cosine squared theta equals 1. So if you divide by cosine squared, you get tangent squared theta plus 1 is 1 over cosine squared theta, or secant squared theta. So secant squared of x squared over 2 plus c, this is x times tangent squared of x squared over 2 plus c plus 1. And y, this is y squared. This is x times y squared plus 1. So y prime equals x times y squared plus 1. And everything checks. So we're okay. Now, you may think this is a hard problem. You may think this is an easy problem. it doesn't matter whether hard, easy. You do have to know calculus well to solve problems in ordinary differential equation. So all the techniques that were used in solving this problem and in checking that the solution is correct have to be tools in your mathematical toolkit. Right? Otherwise, it's hard. Are there any questions about this? This is the fundamental technique for this entire section. And in the subject of ordinary differential equations, the simplest equations are linear first order equations. And the next simplest are these separable first order equations. Right. Let's look at the next example. I mean, the textbook is really quite good, I think, and it's remarkable that it's available legally for free to everyone, and you get a very good book, and you don't have to buy it. So let's go to the next example, which is example 2.2.2. So this equation, this problem has three parts. First is to solve the equation y prime equals minus x over y. Second, to solve the initial value problem. The same equation and the initial condition that y of 1 equals 1. And the third and last part is to solve the same differential equation with a different initial condition, y of 1 equals -2. So we have three problems to solve. Again, this equation doesn't look separable, but if you simply multiply by y prime equals minus x, now this equation is separable. My function h of y is equal to y. My function g of x is equal to minus x. Right? Well, capital H of y, which is the integral of little h of y dy, is just the integral of y dy, is a half y squared. And capital G of x is the integral of little g of x dx, which is the integral of minus x dx, which is minus a half x squared. So the statement that h of y of x equals g of x plus a constant is the same as saying a half y squared equals minus half x squared plus a constant. Or if I put the x's on the same side of the equation, or sorry, bring this to the other side of the equation, that's a half x squared plus y squared equals c, plus a half y squared equals c, or x squared plus y squared, just multiplied by 2, equals 2c. And x squared plus y squared, no matter what values of x and y you pick, is always greater than or equal to 0, because the square is never negative. So I can write, so 2c is non-negative, so I can just write 2c equals a squared. So x squared plus y squared equals a squared. So any solution of this differential equation satisfies x squared plus y squared equals a squared. And we can solve this for y. Y squared is a squared minus x squared. So y is plus or minus the square root of a squared minus x squared. And you only can do this when y is different from 0, because this is the equation, y of x can never be 0. So this is valid for any x, a squared minus x squared has to be positive. So the absolute value of x is at most is less than a. So x is between minus a and plus a. So this differential equation has two solutions. One solution is the top half of a circle of radius a, and the other solution is the bottom half of a circle of radius a. Those are the two solutions of this differential equation. So maybe I'll pause for a minute and give you a chance. I mean, you shouldn't be at a lecture without paper and pencil. Just to go through this yourself right now. Write down the differential equation and step by step solve it. I mean, you can do it because the solution's in front of you, but you need to have a chance to do it yourself. So let's pause for a second and you can review this and ask me questions about any steps you want to ask about. Any questions about this? No? Okay. Let's continue looking at examples. So the next example is the following. Oh, sorry, I haven't finished with this. This is the solution of part A. This is the general solution of this differential equation. But what about the initial value problems? So if you want to find the solution for which y of 1 is equal to 1, then y has to be the positive square root of x squared, a squared minus x squared. So this is for part B. Y of 1 equals 1. So we look for a solution y equals the square root of a squared minus x squared. And to say y of 1 equals 1 means when you let x equal 1, y is equal to 1. So 1 is the square root of a squared minus 1. That means that if you square both sides, 1 equals a squared minus 1, or a squared equals 2, or a is plus or minus the square root of 2. But because all you need is a squared equals 2, so y is the square root of 2 minus x squared. That's the unique solution of the differential equation that satisfies the initial condition y of 1 equals 1. And suppose you want to solve the differential equation with the initial value y of 1 equals minus 2. In that case, the solution has to be negative. That means you're looking at the bottom half, the bottom curve. So the general solution is y is minus the square root of a squared minus x squared. And when x is 1, y is minus 2. So minus 2 is minus the square root of a squared minus 1, which means if you square both sides, 4 equals a squared minus 1, or a squared equals 5. So my solution is y is minus the square root of 5 minus x squared. So this is the unique solution of the differential equation, which when x is equal to 1, y is equal to negative 2. So this is the solution. This is the general solution to the differential equation. This is the solution that satisfies the first initial value problem. And this is the solution of the second initial value problem. Okay. Let's look at some more examples. Fun. So this is example 2.2.2. Sorry. I want to, we just did that example, 2.2.3. So here's my differential equation. Y prime is 2x plus 1 over 5 y to the 4th plus 1. And you can observe that this denominator is never 0, because it's 1 plus something non-negative. That's always nice. If we multiply through by the denominator, 5y to the 4th plus 1 times y prime equals 2x plus 1. So this is my function h of y, and this is my function g of x. So capital H of y, which is the integral of 5y to the 4th plus 1, I just need any antiderivative. This is y to the 5th plus y. And capital G of x, which is the integral of 2x plus 1, is x squared plus x. So any solution, any function y, which satisfies the equation h of y equals g of x plus c, which is y to the 5th plus y equals x squared plus x plus c, any solution of this, any function y that solves this equation, solves the differential equation. Of course, the problem is that we don't know how to solve a degree 5 polynomial. So what we can say is that this equation implicitly solves the differential equation. We cannot explicitly solve for y, but any curve that satisfies this equation is an integral curve of the differential equation. And suppose we look at the initial value problem. We want to find the particular solution of this equation that satisfies y of 2 equals 1. That means when x is 2, y is 1. So 1 to the 5th plus 1 is 2 squared plus 2 plus c. That says that 2 equals 6 plus c, or c equals minus 4. So the particular solution of this differential equation that satisfies this initial value problem is y to the 5th plus y equals x squared plus x minus 4. Okay. Any questions about this? Let me keep on doing problems because these are very nice. This is example 2.2.4. We have the differential equation y prime equals 2xy squared. Now, there's one sort of trivial solution, which is y of x equals 0 for all x. Because if y is 0, y prime is 0, that's the solution. So one solution of this equation is the 0 solution, which is the trivial solution. And if we want to find non-trivial solutions, well, suppose y of x is not identically 0. The y of x is different from 0 for some x at least. So divide by y squared, because y squared at some point x is different from 0. We get y prime, 1 over y squared y prime is 2x. So my function h of y, capital H of y, this is the integral of 1 over y squared dy, that's minus 1 over y. And capital G of x is the integral of 2x, which is x squared. So we get minus 1 over y is x squared plus a constant. Or if you reciprocate, just take the reciprocals of both sides and multiply by minus 1, y is minus 1 over x squared plus c. So if you have, so for this differential equation, you have the trivial solution, y of x always equal to 0. And for any non-trivial solution, y of x has to be minus 1 over x squared plus c. Let's just check this is a solution. It's always nice to check. So if y is equal to this, y prime is minus, so this is like minus x squared plus c to the minus 1. So when you differentiate this, you get minus x squared plus c to the minus 2 times the derivative of x squared plus c, which is 2x. So minus times minus is plus. You get 2x over x squared plus c squared. This is y squared is exactly this. So this is 2x y squared. So you see this checks. Any questions about this? All right. This is all fun. Let's keep going. Suppose we look at example 2.2.5. So y prime is a half x 1 minus y squared. Now this equation also has a trivial solution. Suppose y of x is the constant function 1 or y of x is the constant function minus 1. In that case, 1 minus y squared is 0. So the right-hand side is 0. And the derivative of a constant function is 0. So 0 equals 0. So these are the trivial solutions of this differential equation. Any other solution will have y of x different from plus or minus 1 for some x. So you can divide by 1 minus y squared. So you get 1 over 1 minus y squared equals times y prime equals a half x. Or actually, let me multiply by 2. 2 over 1 minus y squared equals x. And again, you have to use a little bit of calculus. So you learned partial fractions in calculus. 2 over 1 minus y squared, that's 2 over 1 minus y times 1 plus y. So you should be able to write this as a sum or difference of fractions where the denominators are 1 minus y and 1 plus y. And in fact, if you add these two fractions together, put them over a common denominator, you get 1 plus y plus 1 minus y. The y's, you get 2. That's exactly what it is. Right? So this is partial fractions. So capital H of y, which is the integral of 2 over 1 minus y squared dy, that's the integral of 1 over 1 minus y plus 1 over 1 plus y dy. You get some logarithms. Yeah, let me just write this slightly differently. This is the integral of 1 over 1 plus y is the same as y plus 1. 1 minus y is minus 1 over y minus 1. So this is the log of absolute value of y plus 1 over y minus 1. And capital G of x is the integral of x dx, which is a half x squared. So we get, at least implicitly, the solution of our differential equation is the log of y plus 1 over y minus 1, absolute value, is a half x squared plus a constant. An alternative way to write this, I just want to follow the text. This is perfectly correct. An alternative way to write this is, remember, the log of x is minus the log of 1 over x. So this is the same as saying the log of y minus 1 over y plus 1 is minus a half. Just multiply by minus 1. It's minus a half x squared plus a constant. If you exponentiate, you get y minus 1 over y plus 1, and absolute value is e to the k, e to the minus a half x squared. E to the k is just some constant, so I can write this as c e to the minus a half x squared. And recall y of x is not equal to plus or minus 1. So neither of these is 0, and they don't change sign. This is either a positive or a negative. This is either positive or negative for all values of x. So here C is a positive constant, but C can be negative. So you can write y minus 1 over y plus 1 is equal to, right, some constant C, e to the minus a half x squared. And we can take this equation and solve for y. Let me just do it. Cross multiply y minus 1 is y plus 1 times c e to the minus a half x squared. That's y times c e to the minus a half x squared plus c e to the minus a half x squared. So if I bring the 1 on over to the right and this over to the left, I get y minus y c e to the minus a half x squared equals c e to the minus a half x squared plus 1. If I factor out the y, I get this, and if I divide by this, so y is equal to 1 plus c e to the minus a half x squared over 1 minus c e to the minus a half x squared. And that is an explicit solution of the differential equation. Any questions about any of this? Okay, now, in this problem, the differential equation we started with was y prime equals a half x times 1 minus y squared. That's y prime equals a half x minus a half xy squared. That's the same as y prime plus a half x y squared equals a half x. This equation is nonlinear. Remember, in a linear equation of the first order, it's of the form y prime plus a function of x times y equals some function of x. And y occurs to the first power. In this equation, y doesn't occur to the first power, it occurs to the second power. So this is a nonlinear equation. The behavior of nonlinear equations is very difficult, very different, and in general, much more difficult than for linear equations, even when they're separable. So just recall for a second the basic theorem on first order linear differential equations. So that's a differential equation of the form y prime plus p of xy equals f of x. And the theorem says that if p of x and f of x are continuous and differentiable, well, let's just say continuous, are continuous on an open interval AB, and if we have the initial value condition, you want y at some point x0 to be equal to y0, where x0 is in this interval, x0 is between a and b, there is a unique solution. There is always a solution, and the solution is unique. Or I should say there always exists a unique solution y of x that satisfies the differential equation and the initial condition. Let me look at an example, another one, our final example. So this is example 2.2.6. Y prime equals 2xy squared. And we have some initial condition that when x is equal to 0, y of 0 is equal to y naught. So this is not linear, right? Non-linear, because you have y to the power 2. Right? A linear equation only has y to the first power. But it's separable. This is a separable ordinary differential equation. For y different from 0, I mean, there's a trivial solution where y is always 0. If y is different from 0, then dividing by y squared, you get 1 over y squared y prime is equal to 2x. Capital H of y, which is the integral of 1 over y squared dy, is minus 1 over y. Capital G of x, which is the integral of 2x, is x squared. So again, we see that minus 1 over y equals x squared plus c, or y is minus 1 over x squared plus c. So for y different from 0, this is solution of the differential equation. If we have this initial condition that when x is 0, the value of y is y naught, you get y naught is minus 1 over 0 plus c, which is minus 1 over c. So c has to be equal to minus 1 over y naught. So the particular solution of the differential equation that satisfies the initial condition is y equals minus 1 over x squared plus c, which is minus 1 over y naught. If I multiply through by minus y naught, I get y naught over 1 minus y naught times x squared. So this is the solution of the differential equation that satisfies my initial condition. In fact, if y naught equals 0, y is equal to 0 for all x. So in fact, we get the constant solution or the trivial solution as a particular value for y naught. Now, let's just look at this for 1 second. If y naught is negative, then 1 minus y naught x squared is never equal to 0, because it's a 1 plus something which is non-negative. So the solution is valid. So this solution y equals y naught over 1 minus y naught x squared. This is defined to make sense for all x from minus infinity to plus infinity. However, if y naught is positive, then 1 minus y naught x squared, this doesn't make sense where the denominator is 0. That means where x squared equals 1 over y naught. So x can't be equal to 1 over y naught. So this solution is valid around x equals 0 for x between plus 1 over y naught and minus 1 over y naught. Oops, sorry, square root. So for positive, so the initial condition is that x naught, that y is equal to y naught at x equals 0. So we're looking for solutions around 0. And if y naught were positive, you only, this solution is only defined as where x naught is less than 1 over root y naught and greater than minus 1 over root y naught. So this solution is not defined for all x. Okay. So that, in fact, is the complete story of separable first order ordinary differential equations. And you have some homework problems for next week using these equations. But we've really covered the entire theory. So on Wednesday, we'll say a little bit about the general theory of existence and uniqueness of solutions for nonlinear equations. It's a beautiful theorem, but it requires a lot more knowledge of advanced calculus than is required for this course. So I'm only going to state the theorem and discuss the theorem, and again, work out a lot of problems involving the theorem. The section after that is techniques for transforming, it's not always possible, but sometimes it's possible, a nonlinear equation that's not separable into one that is separable. So this is very important in applied mathematics and physics, in any application of differential equations to science or to social science. And after that, we talk about exact equations and integrating factors. And then we'll spend the couple of days about applications of first order equations to science. And then we're on to second order equations. So that is the coming attractions for us. Okay. All right. Any questions about anything that we've done? If not, I'm hesitant about rushing on too fast, so I'm going to stop right here. But this is the entire theory of separable first order equations. And the more exercises and examples you work out, the better you learn the material. I would also want to remind you that solutions to a lot of the homework problems are in the back of the book. And a very good way to learn the subject is to work on the homework problems before you look at the answer, and then look at the answer. And then if you don't have the right answer, or if you couldn't solve the problem, then you look at the answer and then try to figure out how you get the answer. You know what the answer is, and the question is, what do you do with the equation to solve it? Okay. That's what we do. Okay.